Hello friends, welcome to my lecture on variational problems in the parametric form. Sometimes it is convenient and advisable to extremize the variational problem to consider the variational problem in the parametric form. In the parametric form, what we have is we have the functional I where x I depending on x and y, and x and y are functions of the parameter t, and the integral is from t naught to t1 f t x y x dot y dot dt, where x is a function of t and y is a function of t. X is given by phi t, y is given by psi t for t naught less than or equal to t less than or equal to t1. Now, in order that the values of the functional depend only on the line and not on the parameterization, it is necessary and sufficient that the integrand in one does not contain t explicitly, and that is that it is homogeneous in the first degree in x dot and y dot. Now, what do we mean by the homogeneity in the first degree of the first degree in x dot and y dot? Here is the definition. So, the function f will be called homogeneous of first degree in the variables x dot y dot if f x by x k x dot y dot k x dot k y dot gives you k times f x by x dot y dot. So, here you can see in the functional t does not occur explicitly, and then when we replace x dot by k x dot by y dot by k y dot, then what we get is k times f x by x dot y dot. So, we will call f to be a homogeneous function of the first degree in x dot and y dot. For example, if you consider the functional the variational problem I x t y t equal to t naught to t1 phi x t y t x dot t y dot t dt, where phi satisfies the homogeneity condition, this one, then we let us show that it does not depend on the parameterization. That means, if we do another parameterization of this problem, then it remains invariant. So, if let us consider a new parametric representation, say tau is equal to zeta t, where zeta dot t is not equal to 0, and x is a function of tau, y is a function of tau. So, tau is another parameter, and then what we will see is that the integral t naught to t1 phi x t y t x dot t y dot t dt can be written as tau naught to tau 1 phi x tau y tau, and x dot t will be equal to x dot t is dx by dt. X dot is equal to dx by dt. Since x is a function of tau, x is a function of tau, what we have written for that, x is equal to x tau. So, this is equal to dx over d tau into d tau by dt, and so we can write it as x dot tau into tau dot. So, what we will have here is that x tau dot tau x tau dot tau x tau dot tau into zeta dot t, because tau is equal to we have taken tau equal to zeta t, tau equal to zeta t. So, tau dot will be zeta dot zeta tau over zeta over dt equal to zeta dot. So, this is nothing but tau dot is equal to x tau dot tau into zeta dot. So, we will have here x tau dot tau into zeta dot t into and then similarly y dot t is dy over dt, which will be dy over d tau into d tau by dt. So, we will write it as by tau dot tau into zeta dot t, and again what we have here, you can see tau is equal to zeta t, tau equal to zeta t. So, d tau equal to d tau dot t into dt, d tau equal to so dt will be replaced by d tau over tau dot. So, zeta dot is nothing but tau dot. So, we will have here tau dot. So, now then what we will have, so this is same as this, and since phi is a homogeneous function of the first degree in x dot y dot, so phi x by x tau dot tau into zeta dot comma by tau dot tau into zeta dot is equal to this zeta dot times phi x by x tau dot by tau dot, because this tau dot this zeta dot x has a scalar k. So this is of the form phi x by k x tau dot and then k y tau dot. So this will be k times phi x by x tau dot y tau dot. So you can replace this value here. When we replace this value here, then what will happen? This zeta dot will cancel with tau dot, because tau dot and zeta dot are same. So we shall have integral x naught to t naught to t1 phi x by x dot tau dot by x t dot by t dot. This x dot t is same as x t dot, and y dot t is we have written as by t dot. So this is equal to integral tau naught to tau 1 phi x by x tau dot by tau dot d tau. This tau as a suffix and t as a suffix we have added to show that this is the derivative with respect to t and this is the derivative with respect to tau. Now, so you can see here that when phi is a homogeneous function of the first degree in x dot and y dot, then the this is the function is independent of the parameterization. So the integrand remains unchanged with the change in the parametric representation. Now for example, you can consider let us say we know that the arc length from along the line from t naught to t1, if you take the curve, any curve, so this is the point corresponding to t naught, the point corresponding to t1, and then the arc length we know is under root dx square plus dy square. In the parametric form I can write it as, if the curve is given as x equal to xt, y equal to yt, where t varies from t naught to t1, then ds is under root dx square plus dy square, which we can write as dx by dt whole square dy by dt whole square into dt. So the length of the curve from t naught to t1, okay, the arc length is equal to arc length AB is equal to t naught to t1 ds, that is under root x dot square plus y dot square into dt, where x dot y dot are derivatives with respect to derivatives of x and y with respect to t. Now here you can see phi x y x dot y dot is equal to square root x dot square plus y dot square. So this is homogeneous function of degree 1 in x dot y dot, because when we replace x by x dot y dot by k x y dot k y dot, this is k and this is also k. So then this is equal to under root k x dot square plus k y dot square, this is equal to k times under root x dot square plus y dot square. So this is equal to k times phi x by x dot y dot. So phi is a homogeneous function of degree 1 in x dot and y dot. Similarly, the area bounded by a certain curve, if you find the area bounded by a certain curve, then area is given by 1 by 2 integral from t naught to t1 x y dot minus by x dot dt. So this is also here what we have, phi x by x dot y dot is equal to 1 by 2 x y dot minus y x dot. So this implies phi x y k x dot k y dot equal to, you can replace x dot by k x dot, y dot by k y dot, and you see that it is k times phi x by. So these are functionals where the integrand phi x by x dot y dot is a homogeneous function of degree 1 in x dot and y dot. So they are examples of the functionals that we are actually interested in. Now, so in order to find the extremals of functionals of the form where phi does not contain t explicitly and it is a homogeneous function of degree 1 in x dot and y dot, what we do is we get the system of Euler's equation to find the extremum of this functional or extremals of the functionals of this form. We have the system of Euler's equation because x and y are the dependent variable, t is the independent variable. So phi x minus d over dt phi x dot equal to 0, phi y minus d over dt phi y dot equal to 0. But here what happens is that because t does not occur explicitly in x dot and y dot, phi x y x dot y dot is a homogeneous function of degree 1 in x dot and y dot, the two Euler's equations are not independent of each other. While in the case where we have phi t x by x dot y dot and t is an independent variable, x and y are dependent variables, then we have these two equations as independent of each other, and we solve them according to the example which we have done earlier, where we had discussed the variational problem in case where we have more than one dependent variable. So we can solve the problem there. Here these two equations are not independent of each other. So to find the extremal, we must consider one of the Euler's equation and integrate it together with the equation defining the choice of the parameter. Now for example, we have the equation phi x minus d over dt phi x dot equal to 0. Okay, so for example, we will solve one of the two Euler's equations, say for example phi x minus df phi x dot over dt equal to 0, and together with the equation x dot square plus y dot square equal to 1, which indicates that the arc length of the curve is taken as a parameter. Now to solve this equation, we will need the Weierstrass form of Euler's equation, which is 1 over rho equal to phi x y dot minus phi x dot y over phi 1 x dot square plus y dot square to the power 3 by 2, where rho is the radius of curvature of the extremal and phi 1 is the common value of the ratios. So phi 1 is given by phi x dot over y dot square, phi y dot over x dot square minus phi x dot y dot over x dot y dot. This is the Weierstrass form of the Euler's equation. We can solve a Euler's equation by using this Weierstrass form also. Say for example, let us consider this equation. Find the extremal of I x t y t equal to t naught to t 1 x dot square plus y dot square to the power half a square x y dot minus y x dot dt, where a is real, some constant. Now in this problem, the integrand phi x by x dot y dot is a homogeneous function of degree 1 in x dot y dot. So let us see, you can replace phi x y x dot y dot is equal to x dot square plus y dot square to the power half plus a square times x y dot minus y x dot. Now you can see when we replace x dot by k x dot and y dot by k y dot, then what we get is k square x dot square k square y dot square raised to the power half plus a square x k y dot minus k x dot y, which is equal to k times phi k times x dot square plus y dot square raised to the power half plus a square times x y dot minus x dot y, which is equal to k times phi x y x dot y dot. So it is a homogeneous function of degree 1 in x dot y dot. Now you can see here that if you instead of phi you write it denoted by f. Okay, so in this solution we have actually denoted phi by f. So if you write f x by x dot y dot as, instead of phi you write it as f x dot square plus y dot square to the power half plus a square x by dot minus x dot y. Then you can see that if you replace if you write it as f x dot y x dot y dot, then you differentiate it with respect to x, partially with respect to x, what you get is a square y dot, and when you differentiate with respect to y dot, again you get delta square f by delta x delta y dot, which is equal to a square. So this implies f x y dot equal to a square. Similarly, if you differentiate f with respect to y, what we will get is with respect to y minus a square x dot, and when we differentiate it with respect to x dot further, we will get minus a square. So we can say that this is f by x dot. Now in order to find f1, f1 means phi 1. Okay, so phi 1 is phi x dot over y dot square. So f1 is equal to f x dot divided by y dot square. So let us find f x dot x dot. So first we find f x dot. F x dot is equal to 1 by 2 x dot square plus y dot square to the power minus half into 2x dot into 2x dot, and then we have minus a square y when we differentiate with respect to x dot. So this 2 will cancel and we get x dot square plus y dot square raised to the power minus half into x dot minus a square y. Now let us differentiate it further with respect to x dot again. So f x dot x dot. Here we have a product of two functions each containing x dot. So we have to use that formula for product of derivative of a product. So minus 1 by 2 x dot square plus y dot square raised to the power minus 3 by 2 into 2x dot into x dot. So 2 times x dot square. X dot square, and then this is minus a square by this is further we have x dot square plus y dot square raised to the power half into derivative of x dot is 1, and derivative of minus a square by with respect to x dot is 0. So this is f x dot x dot. We can simplify it. We can write it as here it is minus half. So we can write it as x dot square plus y dot square raised to the power minus half, and here we will have minus x square plus y dash, okay, 1 upon x dot square plus y dot square minus x dot square plus 1. So this is x dot square plus y dot square minus x dot square. So we get y dot square divided by x dot square plus y dot square divided by to the power 3 by 2. So f x dot is this, and therefore phi 1, okay, therefore hence f1 is equal to y dot square upon x dot square plus y dot square to the power 3 by 2 f x dot divided by y dot square. So 1 upon, so this will cancel and we will get f1. Okay, f1 is 1 upon x dot square plus y dot square to the power 3 y2. Now let us use Weierstrass form of Euler's equation. So we go to the Weierstrass form of Euler's equations. So 1 by rho equal to phi x by dot minus phi x dot y divided by phi 1 x dot square plus y dot square to the power 3 y2. Now in place of phi we are writing f here, so we have 1 by rho f x by dot minus f x dot y divided by f1 x dot square plus y dot square to the power 3 by 2, and this is equal to f x by dot f x f x by dot we had found. F x by dot came out to be we had found f x by dot is equal to a square. So we have a square minus, and this is minus a square, and then we have f1 into x dot square plus y dot square to the power 3 y2 equal to 1. So we get 1 by rho is equal to 2a square, or rho equal to 1 by 2a square. Now here rho is the radius of curvature. So radius of curvature is a constant quantity, and therefore the extremals are circles. So this rho is the radius of curvature. So we have the radius of curvature of the extremal the radius of curvature of the extremal is a constant, and therefore the extremal is a circle. So extremal, because the radius of curvature of circles is a constant quantity. Now it is the radius. Now what we have is let us now so the extremals are circles. Now find the extremal of this problem. Let us see this problem. So we have integral over t0 to t1, t1 to t2 by times x dot square plus y dot square to the power half dt. So here phi x by x dot y dot is equal to y times x dot square plus y dot square raised to the power half, and therefore we can, and moreover we notice that when we replace x dot y k x dot, y dot y k y dot, then what we get is y times kx dot whole square ky dot whole square to the power half. So this will give you ky into x dot square plus y dot square to the power half. So phi is a homogeneous function of degree 1 in x dot and y dot. Okay, now so the Euler's equations are delta phi by delta x minus d delta phi over delta, we have here x and y are dependent variables, t is into delta phi by delta x minus d over dt of delta phi over delta x dot equal to 0 and delta phi over delta y minus d over dt of delta phi by delta y dot equal to 0. Now we will pick up one equation from the here and find the extremals of the given problem, and then we show that the second equation is not independent of the first equation. If we solve second equation, there also we will get the same extremals. So let us see how we will pick the first equation. So let us take the first equation here, delta phi over delta x. If we find delta phi over delta x, what we will get? 0 here. And if we find delta phi over delta x dot, then what we will get? Y times 1 by 2 x dot square plus y dot square raised to the power minus 3 by 2 into 2x dot. So this 2 will cancel and we will get yx dot over x dot square plus y dot square to the power 3 by 2. So this will give you 0, okay, the first Euler's equation. The first Euler's equation gives us minus d over dt phi delta phi over delta x dot. So by x dot divided by x dot square plus y dot square raised to the power 3 by 2 equal to 0, okay, because this is 0. So now integrating with respect to t, what we get? By x dot divided by x dot square plus y dot square to the power 3 by 2 equal to some constant, let us say c. Okay, now there arise two possibilities. The possibilities are the constant c is 0 or the constant c is not 0. So let us discuss the two cases separately. So we will let us consider the case 1. C is equal to 0. The constant c equal to 0 will give you y equal to 0 or x dot equal to 0. So when c is equal to 0, either y is 0 or x dot is 0. So x dot equal to 0 gives you x equal to some constant, you can say c1, okay. So when c is equal to 0, y equal to 0 could be an extremal or x equal to a constant could be an extremal. Now let us say the case 2, when c is not 0. When c is not 0, then we will get yx dot divided by x dot square plus y dot square raised to the power 3 by 2 equal to c. So we will get here yx dot, okay, yx dot upon x dot square plus y dot square to the power 3 by 2, we will get, we have to solve it, so we will get y square, okay, so we will square it, y square x dot square upon x dot square, we have x dot square to the power del phi over del x dot. It should be minus half, not 3 by 2. It should be minus half here. Because we are differentiating phi with respect to x dot. We are differentiating this is phi equal to by times x dot square plus by dot square to the power half. When we differentiate with respect to x dot, we get by times 1 by 2 x dot square plus by dot square to the power minus half into 2 x dot. So x dot by upon x dot square plus by dot square to the power half. So this is half here. So we get y x dot upon x dot square plus by dot square to the power half, and this will give you, when we square this, y square x dot square upon x dot square plus by dot square is equal to c square. So or we can say by square by c square equal to x dot square plus by dot square divided by x dot square, which is 1 plus by dot upon x dot whole square. By dot is dy by dt, x dot is dx by dt. So by dot over x dot is 1 plus dy by dx whole square. So 1 plus dy by dx whole square. So what we will get, dy by dx equal to y square minus c square under root divided by c, or we can say c upon under root y square minus c square dy is equal to dx. So this will give you, when we integrate this, so or we can say dy upon under root y square minus c square is equal to 1 by c dx. Okay, so this gives you, when we integrate, we get cos hyperbolic inverse y over c equal to 1 over c into x plus 1 over d. Some constant c3 we can write, or we have already taken c1 we have taken. So let us write c2 here. So then what we will get, by equal to c times cos hyperbolic cos hyperbolic x by c plus 1 by c2. So one solution we had as y equal to 0, another solution was x equal to c1, and this is the third solution, y equal to c times cos hyperbolic x by c plus 1 by c2. So there are three extremals of the given problem, which we have found by solving the first Euler's equation. Let us show that the second Euler's equation, when we solve, it also gives us the same extremals. So let us, what we will do is, when we will simplify this second Euler's equation, we shall see that we get this equation, by x dot upon x dot square plus by dot square to the power half is equal to c, which when we solve by taking the case c equal to 0 and c not equal to 0, we arrive at the three extremals, y equal to 0, x equal to c1 and y equal to c cos hyperbolic x by c plus 1 by c2. So we shall simply prove that the second Euler's equation, when simplified, gives rise to the same equation, this one, and therefore when solved, this equation gives us the same extremals. So let us solve this second Euler's equation. So second Euler's equation we need to find phi delta phi over delta y. Delta phi over delta y, if we find, it is x dot square plus y dot square raised to the power half, and when we find partial derivative of phi with respect to y dot, what we will get, by times 1 by 2 x dot square plus y dot square raised to the power minus half into 2 y dot. So this will cancel and we will get by y dot divided by x dot square plus y dot square to the power half. and therefore second Euler's equation gives us partial derivative with respect to y. So 1 upon x dot square plus y dot square minus d over dt of by y dot divided by x dot square plus y dot square to the power half equal to 0. We can write it in this form, or d over dt of by y dot upon x dot square plus y dot square to the power half is equal to 1 by x dot square plus y dot square. No, wait, we have this is x dot square plus y dot square to the power half. X dot square plus y dot square to the power half. So we get here x dot square plus y dot square to the power half Now what we will do is this gives you 1 upon x dot square plus y dot square to the power half into d over dt by y dot upon x dot square plus y dot square raised to the power half equal to 1. Okay, let us divide by x dot square plus y dot square to the power half. Then what we do is we multiply both sides by 2 by y dot. So 2 by y dot upon x dot square plus y dot square raised to the power half d over dt of y dot over x dot square plus y dot square raised to the power half equal to 2 by y dot. Now we can see that the left hand side is the differential of when we differentiate y dot upon x dot square plus y dot square whole to the power half raised to the power half, what we get 2 times y dot upon x dot square plus y dot square to the power half into the derivative of y dot upon x dot square plus y dot square to the power half. So what we get is this also we can write in the following form. Y dot d over dt of y dot over x dot square plus y dot square to the power half equal to d over dt of y square. Okay, we integrate both sides. So y dot upon x dot square plus y dot square this to the power 2. Okay, so this square is equal to y square, let us write plus c square, constant we can take as c square. So what we will get y dot upon x dot square plus y dot square. Okay, this is to the power half here. let me write it again, x dot square plus y dot square raised to the power half whole to the power 2. So, what we will get? Y square y dot square upon x dot square plus y dot square minus y square equal to c square. So, when we take LCM, what we get? Y square y dot square will cancel and we will get x dot square y square x dot square equal to c square, or we will take the square root and we will have by x dot upon square root x dot square plus y dot square equal to c, and this is what we wanted, by x dot upon x dot square plus y dot square to the power half is equal to c. So, second equation also leads us to the same equation, which when we solve we get the extremals as we have got the extremals from the by solving the first equation. So, the two equations are not independent, we can solve any one equation and use the parametric form and the parametric relation and get the extremals. So, this is the second example on this variational form. In our next lecture we shall consider the variational problems with moving boundaries. So far we have considered the variational problems where both the endpoints x1 by 1 x2 by 2 were fixed. Now we shall take the variational problems where either one or both the endpoints are not fixed, they are moving. So that will be discussed in the next lectures. Okay. Thank you very much for your attention.